Okay, so today we're going to look back a little bit at self-propulsion and see basically what systems are out there. So there'll be quite some nice, well, hopefully inspiring examples from literature. So in a way, if you wanna move stuff that's not a natural kind of organism, there's three options that people have used and applied, or a combination of three different scenarios in order to make things work. And the first option is the oldest one of the three. And basically what you have is that you have a particle or an object that releases or consumes a chemical component. And the easiest example is very old. Camphor, which is like a crystalline compound that it's a natural compound, so you can isolate it. So the molecular structure is given on the right-hand side there. People already in 1787 and 100 years later as well figured out that if you have a crystal of this material and you put it on water, it self-propels and it moves around. And obviously there was a bit of a violent discussion on what the underlying reasons were. And the guy that got it right was Professor Tomlinson, in a way, because he stated in his work, very early work already, saying that the movement is due to a difference between the tension of pure water and that of the camphor solution. So imagine that your camphor molecules, obviously, they dissolve a little bit in water, yeah? They basically start to disintegrate from the crystalline surface, and as a result of that, you get a gradient in interfacial tension, and as a result of that, you get induced flow, and as a result of that, the particle kind of moves. So other people around that time thought it was due to electronic effects and all kinds of weird scenarios. So this is the oldest kind of example, at least that I could find, in the literature of something that self-propels. And it's still very popular. This system is still insanely popular. So here, in order to show you that, here you see a paper from 2010 in which effectively they've upgraded the camphor little crystal to a little bit more fun, basically. So they made a plastic plate and then attached a little camphor disc to it, and then they had a circular swimming area, swimming pool in a way, and they put all these little boats in there, and then they just let it do its job, really, and see what would happen. And so the interesting thing here is that you not only have one particular camphor boat, you have a few of them, so potentially they might start to influence each other. So the driving force for one single boat is basically the difference of the interfacial tension on both sides, and as a result of that you get movement. But if the second boat comes closer, obviously it starts to come into the region that there is already camphor present from the other boat, and that would influence the interfacial tension gradient. So you could get a bunch of different scenarios that could happen if you dunk a few of these things in water. So here's a few of the movie clips that you see, and they move quite fast. So either they move quite nicely in line with each other in the left picture, or they start to kind of form clusters with each other, or bump into each other in a way. So if you want to have a closer look at that, you can check out those video clips for yourself. So now this thing is very recent. It's literally a few weeks old, if not a bit younger. It's 2012 date. So and this was quite interesting. So basically what they had was a polyaniline kind of hollow cylinder, which they filled up with zinc. These guys did a different system before, but this system is quite violent in a way. So this is the first example of a hydrogen-powered rocket, micro rocket in a way. So they backfilled it with zinc, and on picture B you see an SEM image of this thing standing up. So you look straight down onto it. So it's hollow. You have zinc with an outside layer of polyaniline, and then basically what they do, if they bring zinc in a very, very acidic environment, so extremely low pH, then you get a reaction between solid zinc and H+, and you start to make hydrogen gas and zinc ions. So you slowly but surely start to disintegrate a little bit of your material. And the plan is that the hydrogen bubbles are quite big, and therefore you just get a rocket in a way. So does this work? Obviously the answer is yes. So here you see these things, and they're very, very fast. So here's a slowed down, 5 times slower. And what you can see is that at the end of this rocket, you get these hydrogen bubbles formed, and this thing moves quite violently through solution. So now you can think, you know, all right, we have a cylindrical type of object, and you can see that the Brownian motion here, you know that the drag force of this object, you have in a way, you've got 2 of them, right? So the least path of resistance is just the way how it travels at the moment. So it doesn't really turn very quickly, but it still turns. So it's still a bit of a random motion. So you don't really have control. It's just something completely getting a little bit crazy. So people have tried to optimize this better so they actually could direct where the flow should go. And you could actually realize this. So this is a slight variety of it. So this is option number 2. So option number 1, a part of your system will actually disintegrate or release something. So in the previous example, you had zinc. Zinc becomes zinc ions. So, you know, slowly but surely you consume your rocket. And the first example, slowly but surely you consume your camphor. And if your camphor is completely dissolved, the system stops. So this example is one of the first, actually. It was published in 2004, but then people weren't exactly sure what the mechanism was, why it actually worked. So in 2006, they had a look at it again. And effectively what you have is an electrochemical cell in one. So you have a rod that's consisting of platinum on one side and gold on the other side. And in a way, you just undertake a redox reaction. So this thing gets fueled by something that's in the medium. So the fuel, in this case, is in the solution, and it's hydrogen peroxide. And on the platinum side, hydrogen peroxide disintegrates in 2H+, 2 electrons, and oxygen. And on the right-hand side, where the gold side is, you get the reverse reaction in a way. So you get like 2H+ plus 2 electrons, and hydrogen peroxide forms 2 molecules of water. So in a way, you have a nice cycle here. And as a result of that, initially it was quite interesting because people thought initially that at the site where you produce oxygen, you would get the same way of moving as in the previous example with the hydrogen bubbles. So that basically would mean that this thing would move to the right-hand side. However, that's not the case. It moves to the left-hand side. And the main reason is that the oxygen production is relatively controlled. It's not completely crazy. But what's more crazy is that you get a hydrogen gradient across. So here you make a lot of H+, and here you consume it. So you get a very, very strong ionic gradient across, which basically means that the system moves in the other direction. So there's still a little bit of controversy about this, what the exact details are, but people start to see, why this really happens. But again, this system will move randomly, right? So it'll move, and if it turns, you don't have control. So they added to these particular systems an extra unit, and that's where option 3 comes in. So option 3, in order to control the way how you move, so this is what happens, if you have no control, you get basically random movement, because you have translational Brownian motion, you also have rotation, and you can't switch off random rotation, and as a result of that, you'll get just random movement. But if you want to switch that off, you can impose an external field. And you can think of lots of different fields, right? Gravitational field is very obvious, but you can only do that with big things. So an electronic field would work, or a magnetic field would work. So what these guys have done, they've effectively made a stripy rod, a stripy equivalent of the example before. And instead of just having gold and platinum, they added a little bit of nickel. And the nickel, if you have a magnetic field across, you basically induce that in the particle. And as a result of that, you only get motion in one direction. So now obviously, you can see it already coming. If you change the magnetic field direction, you change the movement of the particle. So now you've got something that you can remotely control in a way. So you change the magnetic field and this thing just moves wherever you want it to go. So you can swim wherever you want to swim. So that's quite interesting. So 3 options, and those 3 options are generically used a lot and are explored more. So this is very, very recent stuff. Just came out on Nanoletters, and this is taking it a step further, right? So you design your micro rocket, and this one is operating on hydrogen peroxide with big bubbles of oxygen, and then you modify the surface. So people might know that if you would have a gold surface, you can react it with a thiol. Yeah. So a sulfur gold bond is quite strong. So you can put these ligands on the system. So picture number 1, you see you have some hydroxy groups. Obviously that is to make it a little bit more soluble in water. And then you have an acid group over here. And if you basically modify that, you turn it into an activated ester in case 2, and then you can react this with in this case, concavitine A, which is a lectin. And these lectins, they bind specifically to certain organisms. This one particularly likes nasty E. coli cells. So the plan is basically, I have a micro rocket that I can control remotely, yeah, and then I'm going to find an E. coli cell that I don't like. It docks specifically with this E. coli cell because you get a lectin E. coli binding interaction, and then you move it to a different region, and then if you lower the pH and you add some glucose, basically, then you can make this bonding quite reversible, and you can undock the E. coli bacteria. So in a way, what you could do is if you would have a sample that is contaminated by cells that you don't like an E. coli in this case, and the other cells you do like, you can just specifically fish the ones out that you don't want with your micro rocket. So it's a bit far-fetched, obviously, but it's a lot of fun. So let's have a look whether it works. So here's your micro rocket. And the big cells are the ones that are good. The little one, this little one over there, that's a nasty one, and that's the one they want to catch. So obviously it's a bit of hit and miss. So you turn it around, and you go, there you go, and suddenly you get binding interaction, and you take your E. coli away with you. So I thought that was quite cool, right? That gets you in one of the top journals, this kind of fun. So, so well done to those guys, I'd say. So then obviously, you know, there's people that that originally thought, well, you know, Purcell's mechanism was based on a this motion that, you know, sometimes these flagella have a helical type of motion, and this is what this is actually a really nice example from a few years ago. People would try to mimic this, but then obviously with a non-biological system. So what they did is with a specific type of silica disposition, so under a particular angle, you can make really complex, you can deposit really complex shapes. And in this particular case, you can make this really, really nice, well, sheet almost of corkscrew type of silica object. So that's in picture A. And then at the same time, what they did is after they did that, they under high vacuum pressures, you can deposit cobalt on it. And cobalt is magnetic, so they basically made these whiskers and they put some cobalt on it, so now they had magnetic ones. And then basically what they did is they got it off the surface just with a little bit of gentle ultrasound, not too much, because otherwise you shatter everything, right? So they have these objects that are about a micron long, roughly, that are magnetic, and these things swim via a corkscrew kind of motion. If there is not a magnetic field, they just undergo Brownian motion, and that's the picture you see on the right. If you impose a magnetic field, you get the same trick as you had before, and you can swim in one direction, and you can write letters and whatever you would like to do. The movie clips of this, because this object is so small, it just comes across as a dot. Yeah, and basically what they had is, because you get specific deposition of cobalt on one side, you can see the thing blink, and blink, yeah, as in the frequency of blinking is a measure for how quickly it rotates, which was already a trick that Jean-Baptiste Perrin used in his work in order to look at Brownian rotation. Same kind of trick. So it's quite a neat example, I would say. So this one, yeah, we've seen in a way already, right? So we've seen the example I gave before. So this one is inspired by nature. Again, it has this flagella on it. So you have, in this case, you have a blood cell, and attached to that, you have microparticles that are linked together with some DNA strands. And these microparticles are magnetic, and as a result of that, you get this swimming kind of object. And you can see on the right-hand side the motion it can make. So you actually have a real swimmer as it would happen in nature, in a way. Okay. So here you see this particular thing moves a bit like it's doing a butterfly type of swimming movement. So and these objects actually, especially the rocket ones swim way faster than the natural organisms. So if you would have a match between a synthetic one versus a cell, the synthetic one would win. So there's a nice paper by Ozin in Nanoletters, I think 2010, a perspective paper that tells you between the competition between synthetic swimmers and natural swimmers. Okay. Now, this is something where, you know, if you suddenly have control of individual objects swimming, which starts to emerge now in science. So these things that I just showed you is just from the last few years, and people starting to get grips, starting to get hold of, you know, start to understand how this works. You can take it to the next level. So this is really just on the edge, basically, of what's possible. And one of the things that's important is chemotaxis. And chemotaxis basically means that an organism, or obviously a swimmer, can move towards or away a certain other object as a result of a gradient. And as a result, in this case, because it's a chemo, of a chemical gradient. So you have a concentration gradient of a certain component in your medium, and as a result of that, an object will swim towards this, or it will swim away from this, one of the two. And this was discovered in the 1880s by Engelmann and Pfeffer for bacteria. So certain bacteria swim towards a certain region as a result of a chemical imposed gradient externally. So people obviously try to do this also with rod-like swimmers. So there's a really nice paper from Darrell, Veligol, and Sen. And this, in this particular case, published in Physical Review Letters. What they did is they had a gel, like a little bit of a hydrogel, and they soaked it in hydrogen peroxide. And then they just placed it in a Petri dish with water, and then they added these rods that would swim under the influence of hydrogen peroxide. So what you see on the pictures from the right to the left is that there's an accumulation of these nanorods close to the exit of the gel, where the concentration of hydrogen peroxide is higher than in the medium. So these things actually swim towards the gel because that's where the fuel is. So, and you can see there's a nice accumulation of these things. So after, 0.7 hours, you have a bunch of them. And after 110 hours, most of them are close to the gel-like object. So now you can think of ways of, instead of using an external magnet, you could just think of, what if I just induce a high concentration of a chemical species somewhere? Could all my assembled bits swim towards that? And as a result of that, once they swim towards that, then maybe they should form a suprastructure. So that would be the ideal self-assembly, right? If you could do that, so classical self-assembly now, what we've seen with this equilibrium stuff, is all random. So you have these micelles and you have particles, and you chuck them in randomly, and randomly there's micelles and vesicles formed. Wouldn't it be really cool if you could say, all right, I'm going to chuck you in this side in the lake, you all have to swim to the middle, and then you have to form the suprastructure. So in a way, you have to have motility, which we've got. You have to have chemotaxis, which is your concentration gradient, and then they have to form a larger structure. So is the latter thing possible? And the answer is just about. So the latter thing is swarming. So swarming basically means that you get collective behavior of different swimmers into a larger structure. So here you see gold microparticles, And upon the addition of hydrazine in this case, they group together in flocks, like, you know, like a flock of birds or like a swarm of bees. So these particles, they just group together and they swim quite nicely collectively towards each other into, well, concentrated domains, really. And then you might think, oh, you know, maybe that's just a little trick, but obviously this is reversible, so you can make them swim away from each other as well. And there's a little close-up movie attached to this piece of work, which was published by Joseph Wang in Angewandte Chemie in the last month of 2010. So it's really cool. And what you see here is they zoom in quite sharply on the edge. And what you can see slowly but surely is that these things, these small particles start to disperse away from each other back into, like, ultimately, obviously, just a random distribution of particles. So you get a nice reversible behavior of swarming. So I think this is what's possible now. So it's up to you guys to make this better in the next few years, right? So this is what you can do with self-propulsion, and obviously it's really nice if you can introduce collective movement and then actually trigger these things to undergo an assembled structure. So this collective swarming, you could take that one step further. You could say, well, you know, maybe if these things are anisotropic, they literally could just build a suprastructure, and that would be a solid thing. That's been done on a larger length scale. So George Whitesides and his group already in the early 2000s did this with very large mesoscale objects that, you know, they actually through movements could come together and then, you know, form a dimer or a tetramer, depending on which sites were hydrophilic or hydrophobic. So you can imagine that this particular stuff will go into the right direction. Now, obviously, this movie just keeps on repeating itself, but I think it's quite cool. You can really see that these things kind of group together to form more concentrated swarms. Okay.